Two more things that are on the test. This one I'm doing without notes. I always regret that. Let's see how it goes. I gave you an in-class assignment where you had y dt equal to t squared plus y squared. And you had an interval, I think it was 0 to 1. And then y at 0 was equal to 1. And you were asked to do this in Excel, the Euler's method. And then you were asked to do this weird thing with differential. It's in your book, actually. I didn't make it up. But you were asked to do something with what we call differential inequalities. So I want to fill in some of the gaps. I didn't make a video on this, but I was trying to do it in between meetings. Differential inequalities. And there's a theorem that is lined up behind this that's that if you have a differential equation that bounces from below and a differential equation that bounces from above, then the solution of the thing in the center is going to be squished between the two other ones. So it seems pretty reasonable. So if you look at that t squared, that's what's making it impossible to solve this equation by hand. The one we're going to give you on the test, you actually can solve by hand, but I walk you through and ask you to do this same exercise. I don't want to give you something complicated on the test. But this thing here, if I look at the values of t, when t is 0, that's the lowest thing this guy can be, and when t is 1, that's the highest thing this guy can be. So I know that t squared plus y squared has to be less than or equal to 1 plus y squared, and bigger or equal to y squared. If I just put in the lowest thing and then t squared highest factor. So I know that the right-hand side, this thing here, you can't separate variables. Because if you try to take the t squared plus y squared underneath the dy, you've got a t in there. If you leave the y squared and bring it over to the other side, then it's not separating variables. You don't have like a multiplied thing on one side and a multiplied thing on the other. So this thing you can't solve with separation of variables. There's no way to actually solve this that we've learned in class. So this is not something where you can get the answer to. So this is what folks did when they had punch cards and they had to like know something about the equations. And it's always this fear. What if the thing I get back is wrong? What if my code has an error in it and I can't see it? How many times? Well, I guess you're going to find out soon. You're going through the whole math program here. You're coding along. Anybody take sabermetrics this semester? There you go. Take sabermetrics. You'll learn how to code in R really well. But then you have 477. You have these classes that you take that machine learning. Just take those. Take those classes because you'll learn how to code really well. And if you do your 5 years and leave, you'll have some skills behind you that I think people will be looking for. Those machine learning classes will teach you how to code really well. So here you have this, and those two guys are solvable. So I'm going to solve for the lower bound. Which is this guy. Let me write it this way. That one I can separate variables on, so I'm going to separate variables. So I get dy divided by y squared equals dt. Invariably, I always make a mistake on these things. That's why I'm nervous to try this on the board without preparing something. But let's go for it. You have Mathematica. You can actually check your work. Just desolve this puppy and see what it says. But this is y to the minus 2 dy dt. That's power rule. Back in the old days, the good old days when things were easy, add 1, divide by that number. I'll just put that here, is equal to t plus c. So this is integrating. This is separate. And then I get minus 1 over y is equal to t plus c. and I can solve for y. That's just going to be a new c. So I'm just going to abuse my variables and just call that a new c. Minus c is the same thing as plus c. It's another constant. And the initial condition is that y at 0 is 1. So if I plug in y at 0 equal to 1, this gives me that minus c is equal to 1. So that's c. And so my lower bound is, oh, sorry, Evan? There you go, Patrick. You're now the checker. You've been kicked out of the checker. Let me do a double check this. 1 over c is 1. Yes, c is still 1. Let me call it y some L's for lower. That's going to give me 1 over minus t plus 1, or 1 minus t.
Wait, is it not negative 1 over t plus c? And so then the negative 1.
Yeah, but the negative just goes to the t, and when you flip both sides, it goes downstairs.
Okay.
And then when you plug in t equals 0, it just becomes 1. Because the c minus c and plus c are this, it's just another constant. Right. Okay. Question. Not yet, but I plan to make more mistakes on the upper bound still. So the upper bound stuff, not as pretty. I have y dy dt is equal to 1 plus t squared, or 1 plus y squared. That one I can separate variables. So I get y divided by 1 plus y squared is equal to dt. And I do know the solution off the top of my head. That's arctan. I know that because I've used it.
Y squared plus 1.
Yes. It's like a super important function, and they just don't give it enough time in calculus and Jedi. It's used arctans are used in neural networks, so it's used all over the place. Okay, so then I need to have the y, so the y is equal to tangent of t plus c. And then y at 0 is equal to tangent of c, which is equal to 1. So that means that c is equal to pi over 4. Because sine and cosine are the same thing. And so your upper bound solution is going to be y upper is equal to tangent of t plus pi over 4. All right, and I think the question I had for you was about y at 1, which you're going to get using Euler, but to spin you back, you traveled back in time. You took your DeLorean back to the place where they were doing this with punch cards. Exciting. No one would have gone to that movie. All right, so you have punch cards, you don't know what it looks like, but now you have an upper bound and lower bound solution. So you can ask yourself, like, what happens at 1? And I don't even know, like, this came from the book, actually. So if I use so the lower bound, if I plug in, I'm going to, well, was it 1 I gave it to you at? I don't remember now. 0.5. 0.5, okay, that makes more sense. So if I put 0.5 in here, I get 1/2 on the bottom says 2. That's the lower bound. And then the upper bound, pathetic, I'm going to use mathematics. Use mathematics for me, because I can't go in with my computer. But if I put in tangent of 1/2 plus pi over 4, I get something. We could have pranked the class, Theo. I could have told you what this was numerically, and then you could have just stared at it for a minute and go, the answer is this.
Yeah, but you guys would have thought it was cool or something.
Probably.
It's 3.4.
Okay, 3.4. So that tells me that my solution at 1/2 is going to be between 2 and 3.4. Again, like this is something that's in the book. It's important. Like if you go into any, you might, I don't know what you're going to decide to do. Life can take you so many different places. But if you go on into engineering type math, they'll do a lot of differential inequalities, just to see what's going on with their solutions. And the equations get really complicated. I did a lot of this when I was in grad school, just cranking out differential inequalities. I think it's kind of an old thing because the first thing you can do is just run it and see what happens. And with Runge Cut it usually works. And you'll know when something's messed up. Like you'll know when you see the solution that the computer will freak out. So if it's stiff or something, you don't need to do a lot of analytical work to find out something's wrong with the differential equation. The computer will tell you something's wrong with the differential equation. And you'll see it. Like Mathematica might hang. It does that when it doesn't like things that you put in it. So you know something's up with this differential equation that's different. But that's what this is. So what you want is you want your Euler method, whatever it gave you for Euler, to be between y at 1/2 between 2 and 3.4. The reason I kind of like, I'm dismissing this a little bit is it seems like a lot of work to go through for something that you can just run Runge Cut out. But I'm afraid to delete it because that's something that every differential equations class does and has done for years. So I'm afraid maybe there's something that you really need this for, and I'm afraid to delete it out of the class. Okay, any questions on this? What's going on? Oh, another thing I recommend is lay out the steps or lay out an example problem so that when you get to that problem, you're not like looking through your notes. Like go through the YouTube video, lay out these steps of what I did and with this example so that you don't have to like go from scratch and try to see where that was. That's another thing. Like it'll be stressful if you do it the other way.